In this example, we are going to work through some examples of hypothesis testing. All right, now just to save time, I'm not going to write the problem up on the board. I'm just going to read it out. I'm going to read it twice. I'll read it once, and then I'll read through it again, and we'll pull out the important pieces of information. All right, so the first problem, all right, these are kind of long. I'll just go ahead and warn you. This references something that we talked about at the beginning of this collection of videos. All right, where we're talking about that scenario I posed where you're working for a lumber company, so on and so forth. All right, so let's say the tensile strength necessary for construction grade lumber is 3,200 kilopascals. All right, you don't really need to know the unit, but you gather a sample of 100 units and find an average of 3,341 kilopascals and a standard deviation of 716 kilopascals. Test the hypothesis that the new lumber is strong enough at the 95% level. All right, so what we're trying to do here is we've got this new type of lumber, right? We want to make sure it's strong enough before we start selling it for construction purposes. So we're going to get a couple of units. We're going to test their tensile strength, right? And then we're going to use that sample to try to make inferences about our population. All right, so I'm going to read this once more and pull out the relevant details. All right, so the tensile strength necessary for construction grade lumber is 3,200 kilopascals. All right, so that is going to be important, that 3,200. We're going to circle back to that though. All right, you gather a sample of 100 units. All right, so those 100 units, that's your sample size. All right, it says you gather a sample, so if you're gathering a sample, that's going to be your sample size. All right, and find an average of 3,341 kilopascals. So that's your average, that's your mean. And a standard deviation of 716 kilopascals. Right. So that is your standard deviation, right? Your sample standard deviation, so S. All right, and then we're asked to test the hypothesis at the 95% confidence level. So we could state that our confidence level is 95%, or we could state this in terms of our alpha. If we're at a 95% confidence level, we'll be operating at a 0.05 alpha. So alpha equals 0.05. All right, now the last number that we kind of skipped over was that 3,200. So we've got all of this information, right? These three pieces, right? Our sample size, our sample mean, and our sample standard deviation, that comes from the data that we collected, right? So this is going to be what we use to calculate our test statistic, right? Our alpha, or our confidence level, or our significance level, that's going to determine our critical value. All right, the 3,200 is what we are comparing this information to, right? So the 3,200 is the standard, right, for this example. And so if they need to be 3,200 kilopascals, then we would want to check to see if they are greater than that, all right? So we are ready to start our test. We'll do this in kind of just because of space. Actually, let's we'll do it for the next one. So we might end up erasing some of this due to space reasons, but let's just start going through and get what we can get down. All right, so the first thing, all right, our first step of hypothesis testing, if we remember, is to state the null and alternative hypotheses. So that's what we're going to want to do. All right, so usually it is easiest to create our alternative hypothesis first, so that's what we're going to do. All right, we're going to create this alternative hypothesis. So what we're trying to test is that the beams are strong, or the lumber is strong enough, right? What does it mean that for it to be strong enough, right? Well, it's got to be greater than 3,200, right? Its tensile strength needs to be greater than 3,200, right? So that is going to be what we want to do, right? So there are a couple of, well, we're not going to get bogged down in that, right? But our alternative is that the average, right, the population mean for this new type of lumber, right? The population mean for the tensile strength of this new type of lumber is greater than 3,200, right? And we need to make it greater than and not greater than or equal to, because of course that equal to needs to go into our null hypothesis. All right, so mu greater than 3,200, right? That's our alternative hypothesis. Once we've got our alternative hypothesis, we can just make our null hypothesis the opposite of that. All right, so the null hypothesis is mu less than or equal to 3,200. The alternative is mu greater than 3,200, right? Or if we wanted to kind of simplify it, the beams are not strong enough, or the lumber is not strong enough, versus it is strong enough. All right, so once we've done that, that's our first step completed. We'll move on to our second step. That is specifying the significance level, right? We've already had that significance level specified for us in the problem, so now we're just going to move on to the next step. All right, the next step, and I'm going to go ahead and we're going to erase some of this stuff. Probably should have just done that from the jump, but that's okay. All right, so we're doing this at the 5% significance level. Our sample size, well, we don't have to worry about that right now. All right, so we're going to be using our z as our critical value. Let me get us away from this edge. All right, so z, and then we got to incorporate that idea of the significance level in there. All right, since this is a one-tailed test, specifically a right-tailed test, it's z alpha, right? So z alpha, and alpha is 0.05. So z 0.05. We can look on our chart, or if we have them written down, we can go find the critical value. Right, again, probably the easiest way, if you don't just already know them, which I don't expect any of you guys to have those just in your head. Right, but the easiest way would be to go to our t-distribution chart. All right, find 0.05 along the top, go all the way down to that row that has the infinite degrees of freedom, right? And there you're going to see 1.645, right? And remember that we can do that because as the sample size goes to infinity, the t-distribution becomes the z-distribution. Right, at this point, if we want to, we can draw out a little distribution, right? And go ahead and mark our critical value. Right, that critical value is going to define our rejection region, right? One of the reasons that if I suggest you do this first, especially drawing out the distributions is not necessary, but it can be helpful. One thing, if we follow the steps of hypothesis testing in the order that they are, when we get to the critical value, if we go ahead and draw this out, it'll help avoid any confusion between the z-score, the critical value, and the test statistic, right? So when students are first starting this, sometimes they can get those mixed around, right? And so this is one way for us to help prevent that, because if we go ahead and get that critical value and then establish our rejection region, right, there's no other number for us to confuse with it. All right, but there is our critical value. All right, so that's the third step completed. Now we go on to the fourth, which is calculating the test statistic. All right, so if we remember, our test statistic is x bar minus c, that's that arbitrary constant, all right, divided by sigma divided by the square root of n, or, if we don't have sigma, s divided by the square root of n. All right, so x bar we know is 3,341. C, or arbitrary constant, that's the number that shows up in our hypotheses, so that arbitrary constant is 3,200. Then we're going to divide that by our standard deviation, which was 716. And we will divide that by the square root of the sample size, which was 100. So, our test statistic is 1.969. So one, we could just compare the numbers and see, is our test statistic greater than our critical value? Or if we wanted to, we could come and see where our test statistic falls in relation to the critical value on our distribution if we decided to draw it. All right, so in this case, 1.969 is greater than 1.645, so it's going to fall to the right. Right, of that 1.645, well into the rejection region, right, the area in red. So our conclusion will be that we reject the null hypothesis. Right, of course, it won't just be that we reject the null hypothesis. Remember that when we are stating our conclusion, we actually have to state what the conclusion is, right? So we're not going to just stop when we get to the reject the null hypothesis phase, right? We also want to state in kind of English, right, what that means. All right, so our conclusion could be something like this, all right? There are several different ways that you could state an appropriate conclusion, all right? But it might be something like, we reject the null hypothesis and we conclude that the lumber is strong enough, and then strong enough to be used in construction applications, right? So there, that puts into just simple words, right, the conclusion of our test. Right, this is an important step because if you are hired to do these kind of tests for somebody, the reason is because either they don't know how to do it or they want to save their own time by having you do it, and that includes the interpretation. They don't want you to say, we're going to reject the null hypothesis and conclude that the alternative is true. All right? They're also not going to just want you to say, we reject the null hypothesis and then stop talking, because that's not very helpful. They need more details. And even further still, in some cases it might be appropriate to say, reject the null hypothesis, conclude that the average or the population mean for tensile strength of this new type of lumber is greater than 3,200 kilopascals, right? A little bit more technical, right? In some cases that would be appropriate. And then on the test or something like that, that would be fine, or a homework. But also if we just put it into actual, well, what are we trying to get at? That's fine as well. All right, but that is the end of this example. I think we will look at one more, and then that will be it. Well, yeah, that's. Alright, sorry, I got 3 of these and I was trying to determine which one I was going to do. Alright, I've got one that I like, but we're going to do the other one. Alright, so here we go. Alright, so once again, I'll read this twice, put down the important pieces of information. Alright, so this says, you are the owner of a small business and you are thinking about shutting it down. When calculating your profits, you take out a salary for yourself, so you are happy as long as you break even, right? So essentially that's saying that as long as your profits are 0 or higher, right, you're gonna be okay with continuing the business because you are getting paid, right? It's not that you're just running this business and just getting nothing out of it. All right, so using weekly profits from the past year, you find an average profit of negative $75.32 with a standard deviation of $286.19. Use hypothesis testing to determine if you should shut down or not at the 95% level. All right, so this one's I don't know. This one's just got some things that aren't super explicitly stated, right? And we have to figure them out a little bit more. All right, but let's go ahead and read through this again, put down the important pieces of information. All right, so you are the owner of a small business and you are thinking about shutting it down. When calculating your profits, you take out a salary for yourself, so you are happy as long as you break even. Using weekly profits from the past year, you find an average profit of negative $75.32. All right, so X bar, that's X bar, you're negative 75.32 with a standard deviation of $286.19. Right, that is our standard deviation. All right, and we're going to use hypothesis testing to determine if you should shut down or not at the 95% level. So once again, 95% confidence level corresponds to an alpha of 0.05. Yeah, that's fine. All right, so a couple of things missing. We need our sample size. Well, if we look back through here, it says we're going to use weekly profits from the past year, right? So that way, in this case, the sample size isn't just explicitly stated, but if we have weekly profits from the past year, there are 52 weeks in a year, so our sample size would be 52. Right? We also don't really have anything explicitly stated for the arbitrary constant, but we'll get to that in just a second. Right, and by get to that in just a second, I mean right now. All right, so our first step, we need to state our hypotheses. All right, so once again, we're going to start with the alternative hypothesis. Right, so what we are testing, right, we're testing whether or not we should shut down. So, so what we need to do is determine whether or not our profits are below or above 0. I guess really we could also just consider this, right? If we're making a loss, right? If our loss is significant, then we would want to shut down, right? If we don't have a significant loss, that would imply that we are making money or that we are breaking even, right? But so as long as our profit is not less than 0, our average profit is not less than 0, we're going to stay open. All right, so one way that we could perform this test is by testing if our profits are negative. right? So if our profits are negative, if we reject the null and we conclude H1 is true, we should shut down, right? So are we gonna shut down or not? Right? If we reject, we should shut down, right? So if population mean profits are less than 0, we want to shut down this business, right? So that's our alternative hypothesis. The null hypothesis would just be the opposite, so mu greater than or equal to 0. All right, we'll notice that up here we've got this, this was another thing that we're interested in. Are we breaking even or making more money? That's what that null hypothesis is saying. But again, because it's got that equality in it, all right, greater than or equal to, right, we need to put that in the null hypothesis, and so that's why we would format this hypothesis test as we have. All right, but that would be our null and alternative hypotheses. The next thing will be specifying our significance level, right? That's the second step of hypothesis testing. It's already been specified for us as usual, right? So we'll move on to the third step, which is finding or determining the critical value. All right, so once again, we're gonna go for Z 0.05, just like we did in the last example. So if we went and found it on our t distribution, we'd find 1.645. All right, but there is an important distinction, right? Because this is a left-tailed test, we need to be using the negative critical value. So this should be the proper critical value should be negative 1.645. Right, this is another good use, or another reason why we might want to use our distribution. All right, it can help us remember, hey, I'm doing a left tail test. My critical value needs to be in the left tail. I need that rejection region in the left tail, right? So for it to be to the left of 0, it has to be negative. Can help us remember that that's what we need to do. All right, now we come to our test statistics. So we're gonna start with our sample mean, which was negative 75.32. We're going to subtract the arbitrary constant, which in this case is 0. So we could write negative 75.32 minus 0, or we could just not worry about including that 0. Then we're going to divide by the standard deviation, which is 286.19 divided by the sample size, divided by the square root of the sample size, so the square root of 52. All right, so negative 75.32, that's our sample mean. 0, that's our arbitrary constant. 286.19, that's our standard deviation, and 52 is our sample size. Once we plug all of that in, we will get a critical value, a test statistic of negative 1.442. All right, negative 1.442 is greater than our critical value, all right, so it falls to the right of our critical value, and it does not fall into that rejection region. So the conclusion for this test, right, fifth step, I don't think I actually mentioned that last time, all right, but the fifth step's reaching / stating our conclusion, all right, our conclusion here should be fail to reject. All right, so we're gonna fail to reject the null hypothesis. We don't have enough evidence to say that this isn't correct, so but again, that doesn't mean that this is correct, right? It's not proof that the null hypothesis is true, right? We're just saying we don't have enough evidence to reject the idea. All right, so when we fail to reject, that's it. We don't make any conclusions. We could make some inferences. All right, maybe if this is us, then maybe we don't close the business just yet, right? But we can't really make any hard conclusions. All right, one thing I want to look at before we finish this up is, let's say, so this is kind of how things would work more in the real world. So here we wouldn't just, I think I mentioned, we wouldn't just pick one significance level or confidence level. We would kind of compare multiples and just see what the strongest result we could get, right? So if it's if we get a rejection at the 99% confidence level, that's great. We're happy there. If we got it at the 95, we might want to check the 99 to see if we could get that, so on and so forth. All right, but here we failed at the 95% level. So we failed at 95%, we wouldn't check 99, because if we fail at 95, we're going to fail at 99. But we might want to check, well, could we reject at the 90% level? All right, so all that would, and I'm not going to erase all of this, but all that would require right, if we just change this to the 90%, so alpha is 0.10, then our critical value, z 0.10, oh, and now I'm starting to, I can't remember if I know this one yet. I use it so infrequently. I want to say that at the 10% level, our critical value would be negative 1.292. It's something close to that if that is not the actual value, but I don't think I have a distribution sheet anywhere close by, so we're just going to go with that. Put a little asterisk by it just in case that's incorrect. All right, so in this case, we probably already see what's going to happen, but I'm going to draw out this distribution anyways. All right, so then we would put down our critical value, right? So negative 2.92, that's going to define that rejection region. Then we would look and see where our test statistic would fall in relation to that, right? So notice that when we went from, so I didn't erase the test statistic because the test statistic is going to be calculated the exact same way. The only thing that would change going from different confidence levels would be our alpha, and then more importantly, or I guess more significantly, the critical value. That's the only thing that's going to change. All right, so we can see here that we've got our critical value set. All right, we've got our test statistic. All right, now we can see that our test statistic, negative 1.442, is less than our critical value, negative 1.292. So it would fall to the left of our critical value. And into the rejection region. All right, so for performing this at the 10% level, right, our conclusion would be reject the null hypothesis, conclude that the population mean for weekly profits is negative, right, is less than 0. All right, so in this case, all right, that's a hard conclusion. All right, we probably want to shut down because it's not if we could have seen that at the 95%, that would have been a stronger result. But a rejection at the 90% is a stronger result than a failure to reject at the 95%, right? Because we're saying, there is an effect here, right? The mean is less than 0, right? At that, or we could say we're 90% confident that the population mean is less than 0. All right, but at the end of the day, that is hypothesis testing. All right, those are some examples. We didn't do two-tailed, but really the only thing that's different is that you just kind of, you cut your alpha in half, and then you're gonna have two critical values, right? You're gonna have two rejection regions, all right? Other than that, same process, same everything. All right, so this is the last video for chapter 10. If you're in stats 1, then this is the last thing. So hope you guys have enjoyed the semester, and I guess I won't see you again in another video, unless you take a different class from me, right? In that case you might. All right, but anyways, I hope you enjoy the rest of your semester, right, and get out of it relatively unscathed.